Hello and welcome to lecture 20 of Introduction to Computational Literary Analysis, and today we're going to look at social networks in literature and how to quantify them. All right, here we go. All right, so I've already written some of this stuff in a notebook, and I'll just go through this with you a little bit. So I say social networks, but really what we're talking about is any kind of network. And in technical terms, this is called a graph. So a graph in the mathematical sense means not very much apart from you have these two elements, nodes and edges. So a node is like an entity and an edge is like a relation between those entities. So two types of these that we typically deal with are directed graphs and undirected graphs. So an example of a directed graph might be that we have node A and we have node B, and we have in between them a little arrow that just says that there's some sort of relation, some sort of thing happening that is going from A to B. And A and B in this case are the nodes and the edge is the arrow. So the edge is the relation between them. And this is like a one-directional relation. An example of an undirected graph is something like A and then a line and then B. And then in this case, A and B are still the nodes, but the edge is the dash here. So what does this mean in literary terms for computational literary analysis? Well, there are lots of possibilities for social networks or literary graphs. And one of the ones that we're going to deal with is one where the characters are the nodes and the edges are where they appear in the same sentence or in the same paragraph or something. This will tell us something about how they interact. But we could really choose anything that we wanted to for nodes and edges. So for example, we could choose place names that are the nodes, and edges are where these place names happen in the same paragraph, in the same chapter, and so on. So we could also say place names and characters are nodes, and then this would be interesting too for certain things. So I'm going to import a library that we haven't used yet that should be in Anaconda. It's called NetworkX. NetworkX allows us to draw, and I'm saying draw, but allows us to construct these arbitrary graphs. So all we're doing with NetworkX is it's nothing fancy. We're just telling it, here are the nodes that I want to use and here are the edges that I want to use. And it helps us to visualize some of this stuff and deal with it in a programmatic way. So first, why don't we work with the Moonstone, a text that we know and have worked with a lot so far. And it's in text, and it's Moonstone. Oh, it's content text Moonstone. And I'm going to save this to Moonstone. Okay, so first thing that I want to try is I'm going to make the characters into nodes, and I'm going to make edges, whether they appear in the same, let's say, paragraph, because sentence might be too granular for this case, just based on what we know about the Moonstone. All right, so one thing that we should do is we should try to collapse some of the names. And one way to do that is we could write a little function that just normalizes names. And it takes a name, maybe that name is like Rachel Verinder or something. And in that case, we want to return Rachel, and if the name is something like Franklin Blake, maybe we want to return Franklin. I'll need to put these in quotes though. So I'm just normalizing them. So actually I can make this a little bit better by saying, by putting this in a list of some sort. So I could say if the name is in Rachel Verinder, Rachel Miss Verinder, return Rachel. If name is in Franklin Blake or Mr. Blake or Blake or Franklin, return Franklin. If name is Gabriel, and of course there are better ways of doing this, but this is kind of like a quick and dirty way. Gabriel Betteridge, and I think I need colons at the ends of these things. And I'll just write a whole bunch of these and not... Okay, I did that cooking show thing where I wrote a whole bunch of stuff and now it's in the oven and ready to go. So now I can test my function. Normalize name. Let's go with Miss Clack. And it comes up with Clack. I should add one or two more. I'm not being great, and I'm using some first names and some last names there. Great. So it's normalizing them, so it's doing an okay job. If I wanted to, I could have written a dictionary to make this a little bit more concise. Okay, so what we're going to do is go through the text and look for these expressions. And if it finds one, and if it finds one in the same paragraph as some other character, it will draw a line between them. It'll draw like an edge between them. One thing that we have to think about is how are we going to store this data? Okay, well, we have all of these characters. And actually, why don't I rewrite this as a dictionary now that I think of it? Because that would make it a whole lot easier. Okay, so cooking show time. Okay, so I've just refactored this a little bit so it's slightly more concise and a little bit less repeating myself. So now it normalizes names. I can test it again. Great. And it gives me a normal form of all of these names. So so we're thinking about a way to store this data. And actually, so to store this, I should probably actually put this function outside of this data structure because I'm going to want to use this data structure. I'm going to want to use the characters data later. So I don't have a complete list of characters here, but I have a few that I can get from characters keys. And I can put that into a list. And so what I have to think about is I have to find pairs of all of these possible characters. So I have a pair of Rachel and Franklin, a pair of Rachel and Betteridge, a pair of Betteridge and Lucy, a pair of Betteridge and Clack. Actually, Penelope is a good one. Maybe I'll add that. Yeah, Penelope is also called My Daughter by Betteridge. Does anyone else use My Daughter? Probably not, so we could probably get away with that. Okay, so basically we want to have a matrix of every possible character combination. Luckily, yeah, Python gives that to us. Yeah, so it's something that I believe is in the itertools library, which comes with Python. And it should be something called combinations. So let's see what happens. Let's assign that to a variable. Let's see what happens if we run combinations on this character list. Does it need something else? Oh, yeah, R length combination. So we're telling it 2. And then, yeah, what happens if we tell it that we definitely want a list in return? Great, yeah, so these are all possible character combinations here. And we can use this to begin a dictionary. So that dictionary will be that pair, and we'll just initialize it with a count of 0. Yeah, now one thing is we have Rachel and Franklin. Do we also have Franklin and Rachel? We have Rachel and Betteridge. Do we also have Betteridge and Rachel? No, so there are no repeated elements here. We have Lucy and Clack, Lucy and Cuff, but Cuff and Lucy doesn't exist. Okay, great. So yeah, this is what we want. So character pairs, we can call this. And now what we want to do is simply just go through all of the paragraphs and say, you know, if this pair of people appears in the paragraph, just add 1 to this list. And in fact, yeah, I can leave this open for a second. Okay, so Moonstone paragraphs is, I'm just going to break this up, split by \n. And I'll just take the length of that to verify. Okay, 3,000 something paragraphs, that makes sense. Okay, now I'm going to write a little for loop that says for paragraph in Moonstone paras. Now I test for the presence of like any of these names. So luckily I have this data structure characters, you know, and so characters looks like this, and so characters values is just like this list of lists that represents like all of the possible character names. And yeah, so we could go through, we could flatten this list if we wanted to. Yeah, I'll just do it this way. I'll call it all characters, and I'll make it a new list. And I'll say for character list and characters values for character name in character list. All I'm doing here is just flattening this list by making one big list that contains all of the character names, so that rather than having a list of lists, I just have a list with all of the names in them. And yeah, now let me just make sure that this is my full list of all of them. Okay, great. So now down here, I want to go through that list of all characters. So now I'm going to test for the presence of that character. And now, so I'm going to use the end keyword, but this is a little bit dangerous because I'm just comparing the string and I'm not comparing anything else. And so if we happen to have an issue, like let's say, for example, cuff was in a paragraph, but also there was the word cufflinks. Or something similar, you know, it would pick that up because it's not looking for tokens. It's just looking for it in the string. But we're going to take advantage of the fact that we know that there are no cufflinks here, and that these names are more or less unique. So if that character is in Moonstone, well, actually, you know what? We don't want to go through all of these characters because we want to go through each possible pair. So yeah, let me do that instead. For character in char pairs, if that character's, if character 0 is in the paragraph and character 1 is in that paragraph, then we're going to say char pairs char. Actually, I'll call this char pair. So char pairs char is the pair that we're on. And then I can increment that by 1, saying that I've seen them. This just says I've seen these two characters in the same paragraph. Okay. Naming issue. Okay, so now if I look at this, yeah, so Rachel and Franklin were 83 times in the same paragraph. Rachel and Betteridge were 26 times. Actually, but we're not normalizing these. So yeah, we are not normalizing these. So yeah, really what we want is to go through the character list and normalize them. But, you know, yeah, just for the sake of time, I'm not going to do that right now. Because I gotta get to the good stuff, to the network. Anyway, so we have basically the graph right now. So we have nodes. So Rachel is a node and Franklin is a node. And 83 is the weight of the edge between them. And Rachel and Betteridge is a node, and 26 is the weight of the edge between them. And some of them are just 0. But this is enough to start with. So NetworkX has this graph module. Yeah, and yeah, that's right. It has this graph object. So I can initialize it just by doing something like this. Are there any options that I could give it? It says it's a base class for undirected graphs. So yeah, that's what we want. So what can we do with this graph? So I can add nodes and I can add edges, and I can do this thing where I can add nodes from something. So this means that I can add multiple nodes from like some sort of a list. So yeah, what is a good list? Well, yeah, let's use the normalized names. So it's characters, keys, and then we can make a list out of that. Did I already do this somewhere? Yeah, I did. It's called chars. So I can say add nodes from chars. And it's done it. It's sort of silently succeeded. And now if we were to look at nodes, it would tell us that, yeah, all of the characters are nodes in this graph. So now we can add edges from. And now how does it want us to add edges? Well, yeah, maybe we can just do it this way. We can add edges. Yeah, just add an edge, like a single edge. So this adds an edge between node 1 and node 2, and then optionally it will let us add extra data to that. So we can give it, you know, any kind of arbitrary data, like we can say weight, length, capacity, stuff like that. So let's call this weight. So we're, you know, if we were to do this manually, it would be something like Rachel, Franklin, and then 83. Yeah, but we're not going to do that. So we're going to go through char pairs. So each one is going to be the pair and the weight. And we can go through the items. So now we're just going to go through each one of these lines, you know, and then this becomes char pair, and this becomes weight. Or, yeah, pair. So that one becomes pair, and this one becomes weight. So once we have the pair and the weight, then we want to take our graph and then add our edge to it. So our edge will be from pair 0 to pair 1, and then our weight is going to be the weight. Yeah, did I call that something different? Yeah, capital P. Yeah, so what do edges look like now? So now I have all of these edges. Actually, you know what? Maybe we should have done this slightly differently. Maybe we should have said if the weight is greater than 0, then add the edge. Okay, so I'll redo this. Reinitialize that. Yeah, because we don't want to add an edge if that is just 0. Okay, so NetworkX has a whole bunch of other toys in it. One of them is, I believe, like draw network or something. Yeah, draw NetworkX. Yeah, what happens if we just run it on its own? Great. We can also give it, we can also change the parameters here. We can tell it that it's a directed graph, that it needs labels, that it, should tone down the colors a little bit. And I believe this is also like a matplotlib. It's a matplotlib chart. So what we could do is just, I'm pretty sure we could just say, hey, let's make this bigger, and it will just do that. Maybe it won't. I don't know. Okay, it doesn't seem to care about that. Yeah, so what it's done is pretty much what we expect. It puts two nodes really close to each other if the weight of their edges is really close. So Franklin and Rachel are two characters that I think appear the most, because of their romantic relationship, the most in the same paragraphs with each other. And then Rachel and Godfrey have this additional side relationship here. Penelope and Betteridge, I would expect to have the closest relationship, but it's actually, Penelope is kind of a linchpin between a whole bunch of people, it seems. And Clack is, of course, most connected to Godfrey, but a little bit less concerned with Rachel and with Penelope. And Ezra Jennings is, of course, connected to Godfrey and Mr. Candy and Betteridge and Franklin and Rachel to some degree. And Limping Lucy is most connected with Cuff and Betteridge and Penelope. So this kind of, I don't know about you, but this kind of represents to me what I would sort of think of as like a good social network for the Moonstone. And all we've done is just look at whether these characters appear in the same paragraph as one another. But let's take this up a notch. Why don't we try something different, like with place names? So, one thing that we could do is we could bring in Spacey as our way to find all kinds of place names. So I'm going to import Spacey, and then because I like to do this up top, I can call this NLP, and I can say NLP equals Spacey load in core web LG. And while that's working, I'm going to say Moonstone doc, I should put that down here, is NLP of Moonstone. And that will take a long time to run, but while that's running, I can get Moonstone locations by saying, like, find a word for each word in Moonstone doc if, maybe I should say ints for entities, if the label is GPE, because I think that's geographic entity of some sort. Okay, has this finished running? Yeah, so you will get this happen at some point, I think. You could run out of memory. And there are some ways to fix this or to get around it. So one way is, if your computer has a lot of memory, you can just increase the max length. So the current max length is 1 million characters, but it's saying that it can only that the moonstone is a little bit more than that. So why don't we just up that just a little bit, 1,100,000. And of course, there are lots of other ways of getting around this. So one way is if you keep running into memory errors, you can do whatever process you're doing just on chunks of a text at a time. And just keep moving that window. And if it's a matter of like a statistical analysis, sometimes what you might want to do is just randomly sample parts of a text rather than deal with the whole text at a time. And sometimes that's even better for certain purposes. Okay, fingers crossed. Meanwhile, okay, and it's done about a good minute or two after I ran it. Okay, because it's computing a ton of stuff. So what is this going to look like? All of these locations. So yeah, quite a lot of locations. We could do the same sort of social network just on locations alone if we wanted to. And so if a location is in the same paragraph as another, we can draw an edge between them. So one thing is we could make a list of just all the locations. However, I'm realizing now that that doesn't work because these aren't strings that we're dealing with. So we have to get the text of each of these. The detective police, that doesn't sound, some of these definitely don't sound like locations. Not at all. You know what? We could just get rid of all of these if we want. And I know a way to do that. If w text is lower, is that going to work? No. Yeah, is capital. Yeah, what is the thing that we're looking for? Is title. I'm pretty sure it's is title case. Okay, so that's false. Now what if we make the first letter? Okay, now what if we make more than one letter? Okay, yeah. So is title is the one that we want. Here, we could have written something like that ourselves, but this is useful. Great, so now this is mostly the locations that we want. Maybe we want to make that set into a list. All right. Great. Why don't we do the same thing where we make a combination, of all of the possible combinations here. So combinations for all lokes. Oh yeah, and we're saying we want 2 of them, and we are going to put this into a list. Yeah, that looks about right. And then we are going to say location pairs is the name of this thing. And now we can say for location pair and location pairs. Actually, first, I can make this a dictionary. And let me just make sure that I did that correctly. Okay, so now I'm going to go through each of these pairs, and actually I'm going to go through each of the paragraphs. And then I'm going to go through each of the pairs. And then I'm going to say if pair 0, which is the first item in the pair, is in the paragraph, and pair 1 in that paragraph, then I'm going to take my count, which is loc pairs pair, and I'm going to increment it by 1. Wow, that's actually taking quite a long time. Great, yeah, so it's saying England and London appear together 11 times. That's kind of unsurprising. England and Penelope 3 times. So, it thinks that Penelope is a place. Now I kind of want to know, is Penelope also a place in real life? Someone get back to me on that. All right, so yeah, we'll do the same thing where we make a graph out of this. So it's like NetworkX dot graph, and then we'll say graph add edges from, and then that's our loc pairs. And yeah, why don't we try that first and make sure that works. Oh wait, it's not edges that we're trying to add, it's nodes. Great, and yeah, we want to add an edge under certain circumstances. So for each of those pairs, we are going to add an edge from the first item in that pair to the second item in that pair. And we're going to give it the weight of yeah, I actually have to do this. It's funny, I just did this. I should just copy and paste what I just did. So it's pair and weight. And now let's look at our graph if it created that correctly. So I think we have to do NetworkX draw NetworkX, and then we give it that graph. And it's taking a long time because it has a lot of stuff to do. Actually, rather than wait for this for a long time, I'm going to, I forgot that, yeah, before I did this thing where I said, if the weight is greater than 0, then add that edge. So I'll redo this. And that should take a little while. And yeah, anyway, just while this is working, I kind of want to say that these are not the only graphs that you can make. Obviously, you can make any kind of graph that you want, from any word to any other word. And you can do it even better by not looking at the strings, but by looking at the tokens. Is token 1 and token 2 in this paragraph, or in this sentence or something? And if it is, then draw a line between them. You can also make it less than binary. And so, like, rather than saying, if it is in the same paragraph, increment 1, you could say, you could measure the distance between them. So you could say, have a place name and a character name. And if there are 3 words away from each other, then mark that down as 3 or mark that down as 4 or something, rather than just have it be like a binary thing. And then you'll get slightly more granular results out of it. This is taking forever. Oh, I see why it took forever. It has way too many points here. So I definitely did something wrong. What if I just redo all of this? It's still taking way too long. So let me look at the nodes. Just so I know what I'm dealing with. Yeah, there's a lot of extra stuff at the end there. So something is up. At some point here, I might have run something twice and it might have duplicated all of the data. So I'm just going to come up here and redo all of this in the hopes that it won't be so crazy this time. How many of these do I have? 1,000 pairs. I mean, that's quite a lot. That's maybe too much. So why don't I take a small subset of this? So what does the first 15 look like? What if I took just the most common ones? So yeah, what if I did a counter of this and did the most common 10, and of course I have to go all the way up to the top and import the counter from collections. This is good when I mess up like this, because it can show you that, so much of this process is really just trial and error. It's just, oh, this isn't working. Why is this not working? Like, let me investigate this. It's probably most of this really is just debugging stuff. So it helps to have, a lot of patience when it comes to this. Okay, so now I should have the most common ones, but what if I don't want the counts? I just want the keys. So can I do this? Can I force it into a list? I'm almost there, so I just want the first one. So for each of those pairs, I just want the first one for pair in all looks. And then what does that look like if I spell it correctly? Whoa, that is not what I thought it would be. Okay, yeah, that's what I thought. Okay, what it was doing is it was getting the first letter of each of these, it looks like. Okay, now how many pairs do I have? I have 45 pairs. Still a bit. Still a bit. What if I brought that down to 7? Now I have 21 pairs. So now if I try to draw a graph, it's a little bit better. Something is still not quite working though. So for nodes, it's getting pairs, but yeah, it shouldn't get pairs. It should just get just the nodes itself. So this should actually be all looks. Okay, yeah, those are the nodes that I want. And now I can add the edges to that. And now I can draw it. Okay, I mean, this is kind of interesting. We have Amsterdam as kind of only in a category on its own. And then London and England and India are really connected. And then Brighton and Yorkshire are kind of over here. And Hampstead is over here on its own too. This isn't quite as meaningful as I had hoped. Maybe let's adjust the parameters here just a touch. So what happens if we look at 9, then we have 36 pairs. This is a little bit better. Here for some reason Amsterdam is appearing twice. Yeah, so it would take a little bit more debugging for us to get something really good out of this, but I just wanted to show you that there is something pretty magical about the simplicity of an approach like this, which is just that you can take any elements and you could see whether they happen together or whether they have some kind of relation, any relation at all, really. And you can graph that in a sense. And you can give it attributes like weight or length or whatever you want. And NetworkX in the background will do the work of visualizing this for you. And it's only just taking the weights, that you give it. And there are lots of other ways of configuring these charts too, so that you can make them more readable and so that you can make them represent different aspects of the graph. So that's it. That was just to give you a little bit of a taste of what you can do with graphs and with network analysis. There are also plenty of other things that you can do where you can take a graph and you can get statistical information out of it. So one thing that you can do is you can compute the there's an eigenvector centrality computation that I'm not seeing in here, but you can have it say like, okay, well, which one is the central node here just based on the number of connections it has. And I'm not seeing it there, but if you look through the NetworkX documentation, and I can help you too to look for this when we talk about it on Zulip, you can find all kinds of statistical measures for what a graph is doing mathematically. And this can tell us something about the text, in many cases something that we already know, in many cases something that's new. All right, that's it for today. Looking forward to talking to you more about this on Zulip.